Welcome back. In the last video, we showed how the actuator could accommodate some quite sophisticated set manipulation. In this video, we will demonstrate how the actuator deals with Monte Carlo models. These are incredibly complex and can easily contain many hundreds of random elements. They are typically used when pricing certain types of financial derivatives and for evaluating risk. The underlying algorithms are so difficult to code that Wall Street software engineers are often referred to as rocket scientists. In this video, you will see the mathematically elegant solution that we developed to represent these models. And as with everything else from the actuator, there are no logical instructions required from you. The actuator does all of the work behind the scenes. We'll cover some rich and powerful concepts, so buckle up and we'll jump right in. The first thing to note is that any model can be converted into a Monte Carlo model by simply specifying one or more of its numeric elements as random. You then jolt these random variables over perhaps 1,000 or 10,000 trials in accordance with various probability distributions. You can see here that our random model contains several additional tabs. Here you see the random parameters tab that allows you to specify the number of trials and the seed. We have the same model tabs as before, but we have some additional random summary tabs that allow you to specify the results that you want to show summaries of the simulation. Let's go back to our simple, coherent underlying model. Any one of these numeric elements, the array, the number, the set numbers that you see specified here, any one of these can be specified by a random variable. Obviously, when you specify something as being random, anything that contains it will also be random. Let's take a look at a simple example. We'll put a random number in here. First thing you notice is that it turns green, and not only that, but everything that contains it turns green also. These are all obviously random. Anything that's not green is not random. The random variable here needs to have a probability distribution specified. If we look over here, let's pick the normal that everybody's going to be familiar with. And here for the normal distribution, you just simply have to specify the mean and the standard deviation. Let's say we want to specify a random array. So we come over to here, put that in here, and you can see that with a random array, we need to specify the probability distribution that governs the behavior of all of its elements, as well as the number of those elements. Same thing happens with sets of numbers. We put a random number set and put that in here. You need to specify the probability distribution, but also the size of the set. Let's go look at tab B, where I've pre-populated this model with some other random variables. You can see here I've put a random array here. We're using an exponential distribution with lambda equal to 4. If you look over here, we've got a mean, which is a mean of a random set of numbers. And that random set of numbers contains 50 elements. It's governed by a geometric distribution with p equal to 0.8. Over here we have something a little more interesting. This is a random number. If you open it up, you see we have a normal distribution. And the normal distribution has a mean of 0, but the standard deviation is itself governed by another random variable. It's a simple random number. This is a Poisson with lambda equal to 3. So you can see that we can put together some quite interesting and complicated structures. I'm going to show you one other structure which is called a rank correlation. First, I'm going to clear this out. What we need to do is specify the probability distribution, then the random variable that we're correlating with, and you can also specify a rank array that helps to drive the shape of that correlation. This basically allows us to correlate with another random variable that's not based on a normal distribution. Okay, here's where it starts to get really interesting. I'm back in the basic model tab. You can see that I've got an element here called the trial number that you can reference anywhere in your model. But we've got a couple of simple structures set up here. Here we see a mean, and the mean is applied to this random number set, which is driven by a beta distribution with alpha 3, beta 7. There are 5 elements in that random set, and we're basically taking the mean of those 5 elements. Now we're going to do that 10 times for each of the 10 trials. So here we have a diagnostic that summarizes that mean 10 times for each of the 5 elements. If we go over to the random summary tab, we've got some other diagnostics set up. Here we've got an all-at-once diagnostic that basically shows all of those 10 means all in one screen. We also have something here where we've taken that mean, those 10 items, and we've selected the largest 3 elements of those items. So we're doing some set manipulation on the output of a random model. And this large N, we've summarized it here in another one of these all-at-once diagnostics. So we're going to see 10 numbers summarized here, 3 numbers summarized here. And then once we take those 3 numbers, you can see they've been summed up and they're being summarized here in this other diagnostic, which is called a show singles, that basically allows you to look at one single number. So basically we've got a lot of diagnostics here, so there's going to be a lot coming at you. Let's see what we get. Let's go back to the model so you can remember. There's 10 items going to be shown here, one after the other. Then we come to the tab here. We're going to see the 3 largest items here. We're going to see all 10 of them here, and this is going to show the one number, which is the sum of those 3 items. Let's hit the actuate button. So here's the first of our means. 1, 2, 3. Now you can see all those 10 items summarized here. Next, you can see the 3 largest of those 10 items. And if you add those up, you can see that's about 0.9 or so. And there it is. There's the 0.987. Now, you would never do this in a normal model. I'm doing this just to show you. But what's interesting about it is that you can delve into almost any element of a model and see the moving parts, see that it works, confirm for yourself that everything's going as it should go. We also support what is known as nested stochastics. That's one random model running inside another. In other words, for every one of the 1,000 trials, for example, for each one of those trials, you'll run 1,000 trials of a nested inside stochastic model. This is often used to evaluate hedging and some other advanced financial techniques. Let's take a closer look. As before, we have random parameters. We have a model here. But with a nested stochastic model, if you come across to the right here, you can see that we've got inner parameters. We've got an inner model here. Now, to distinguish random variables from one model, the outer to the inner model, you can see that we use slightly different colors here. They're yellow instead of green. And basically, any element in the outer model can be used as an input to the inner model. And then eventually, any output of the inner model in an inner summary could then be used finally to feed back to your outer random summary. It sounds complicated, but it is complicated, but believe me, programming it is very complicated. This is about as simple as you can get it. So let's take a closer look at this. Here I just have a simple mean as before. It's a mean applied to a random number set. This is a gamma distribution. And in my inner model, again, I have trial number. Here I'm looking at the minimum of 2 values. This is the minimum of 2. Here's a random number, and it's a uniform distribution. You can see I've got a maximum of 100. This minimum could be referenced against something from the outer model. So, for example, if I took this mean, I'll just copy it to the clipboard here, come back to the inner model, and if I come down here and I paste that link, you'll notice something interesting. You'll see that this uniform distribution is now random only from the outer side, but this is random according to the outer and inner model. And you can see that it's yellow and green all the way up. And we use these colors to help you distinguish which elements are random within the inner model, within the outer model. And again, as we go all the way out to the summaries, we keep track of all these things. Now, if the hardware ever catches up with us, we also have a triple nested stochastic model ready to go. In that particular case, we use a mauve as our shade for the inner model. We also have other special random longitudinal models for things like COVID and queuing models. These are structured a little differently, but they all use the same inverts. You can see by now that the actuator is not a toy, not just some kind of low-code, no-code tool, but a tool for building software of astonishing complexity. If you've worked with these models, you will know how difficult and time-consuming they are to build, but the actuator does it in seconds. We're indeed in a new world. In the next video, we will show you how the actuator can be used to perform some sophisticated financial calculations. We'll see you then.